So the next speaker is Professor Chien-Ling from Johns Hopkins, and he will talk about spin triplet superconductors.
Okay,
Yeah.
thank the organizer for inviting me. And this morning we started with Maury physics and gradually moving away from Maury. So in my talk, there's no Maury, only superconductivity. I'm from the William H. Miller III Department of Physics and Astronomy, okay? Quite a mouthful. Uh, well, Okay, this is a brief outline of my talk. I'll give some introductory remarks. And I mentioned that there are lots of singular superconductors, but very few triplets. Why triplets are important. And we have developed phase-sensitive methods of detecting triplets. And you will see on the left-hand side a wedding ring. So you understand soon why there's a wedding ring. And on the right-hand side is the results of the so-called half quantum flux and how they're related to triplet superconductor. Okay, in short, I try to achieve unequivocal identification of triplet superconductor. At the end, you can judge for yourself whether we have achieved that. Why is triplet superconductor important? The theorists told us that Mariana fermion live on triplet superconductor, and which are important for fault-tolerant quantum computing. Okay, superconductivity involves Cooper pair, a Cooper pair of 2 electrons, and therefore they can form a singlet which spins 0. And on the far left is the S wave, which are the superconductor we're most familiar with, where the gap is constant and does not change sign. So you can do inversion, the value remain the same. And the high DC are the D wave, which also have even parity, but in this case, the gap value changes value, and if you turn 90 degrees, the gap value changes sign. So, and the 2 electrons can also form spin 1. That becomes the triplets. And triplets have R parity. By that I mean, if you now make an inversion, the gap must change sign with a minus sign. Right? And historically, we know helium-3 is a triplet. It's a superfluid. For many years, people believe strontium-ruthenate is a triplet. Unfortunately, that prospect has died recently. So all the superconductors we're familiar with are BCS superconductor. Okay, they are the singlets. Anything that's non-BCS are collectively called the unconventional, which includes all the exotic ones, including the triplets. So unconventional does not necessarily mean it's the triplets. Okay, how to distinguish triplet superconductor? Okay, we all know the superconductor has wave function, there's the magnitude, also has the phase. Most of the time, people use amplitude-sensitive method. These are the methods people have used over the years, way before, decades before. The most common one are upper critical field and the NMR night shift. Right? And the phase-sensitive method involve trying to address the question whether the gap has even or odd parity, or if one can measure the Cooper pair spin, or measure time reversal symmetry. Right? So now we ask the question, which triplets that we can ascertain? If you look at what people have done, upper critical field is the most common technique. People have used it for many years. That is, any critical field greater than the Pauli limit, 1.86 TC is a triplet. So this is the red line, the Pauli limit. Every superconductor above this line, if this method is accurate, is a triplet. If there's only a few, they're triplet, that means this method is not reliable, right? The strontium luteinate is just below this critical line. So my conclusion is this method is not reliable. NMR night shift used to be the smoking gun evidence for strontium luteinate at the triplets because they measure the night shift. There is temperature independence across TC. So there's no change. This is considered the smoking gun evidence for strontium luteinate to be a definite triplets. That was 1998. 2019, they made better sample. They do better measurement. It showed very distinct temperature dependence. Overnight, it died. Strontium luteinate is no longer considered a triplet superconductor because of the night shift temperature dependence. So I don't want to use these methods because they show it's not reliable. So my conclusions, or our conclusions, if you can measure one of these three quantities, you'll be able to say. If you can measure the Cooper pair spin, gap parity, or time reversal symmetry, you can say. And today we'll discuss one of the three. That is, we measure the gap parity. We are working on the two methods, and before we're successful, I won't tell you whether it works. Okay, here comes the wedding ring. So if you have a superconductor, if you apply perpendicular magnetic field, the flux must quantize. The flux coming from the external field as well as the phase change in the superconductor must end time phi naught. Right? This is the Little Park experiment. When I was a student, I considered this is the most impressive experiment that I have ever encountered. Little did I know, many years later, actually doing that myself. Little Park experiment is not an effect of small Parks, okay? Little is a professor, Park is the graduate student, and Park is not Korean. Okay, so if you measure the resistance of a superconductor ring at temperature just below Tc, you will see resistance minimum. Minimum occurred at integers times phi naught. What is phi naught? Phi naught is a flux quantum. If you have to make a fundamental constant, h over e is sufficient. But it has to be h over 2e because nature tries to tell us Cooper pair have charge 2e. That value is 2 times 10 to the 15 Tesla meter square. I use an R-ball and unit called 20 Gauss per micron square. It tells you this ring must be around 1 micron in air square. Then the oscillation occurred at 20 Gauss. If you make the ring 100 micron by 100 micron, you're talking about 2 milligauss. To me, you can forget it. Too hard, okay? So the key is you want to make a ring of the order 1 micron or submicron. Then you will see, this is the first experiment, okay? They are very clever. They did not have lithography that use a filament 1 micron size, electroplated tin, and measure it. And in those days, oscilloscope trace is good enough for PIL, not anymore. So integer flux quanta in S wave, they demonstrated. They actually demonstrate Cooper pair actually charge 2e. Right? And the subsequent years, this is high TC, YBCO, polycrystalline, epitaxial, they all show integer. No exception, always integer, because in all the singlet, flux quantization is always integers times phi naught. Okay, this is our work. We use niobium. Of course, we see integers phi naught. Our size is submicron, okay? So the oscillation occurred at 30 Gauss. That's very easily you can see. Now, let's suppose you have a triplets. And let's suppose you have a green boundary. It's not a single crystal. Let's suppose that green boundary has, because the green boundary has a change sign. Theorists tell us, these are the three theorists, Gershkenbein, Larkin, and Barone. Let's call it GLB. They predict in 1987, if you have a green boundary change sign, you have a pi junction. That means you already have a pi shift. Your external field must provide so that you still have integer flux your oscillation will occur at half integer. 1/2, 3/2, 5/2. Right? This will be the key evidence for a sign change in the gap value. Right? So this is why half quantum flux occur in triplet superconductor if you make the ring out of that. Right? Okay. So the integer, as I mentioned, is already measured, observed in all the singlet. The half quantum should be observed in triplets if you can find a triplets. In fact, the half quantum actually has been observed. If those of you are old enough like me, gone through the high TC days. Chien discovered D wave using exactly this theory, make a tricrystal, make the in the apex, you will see half quantum. Van Harlington in Illinois, they make a corner junction with 90 degrees. They also saw half flux. So we need to remind ourselves, high TC D wave is not using thermodynamic measurement. It's using phase-sensitive measurement. That is the reliable method, not thermodynamics. Okay? So, which triplets? Okay, we try. Theorists suggest topological superconductor might be triplet. So we try various. I won't tell you the failure. I'll only tell you the success. This is the success. Beta bismuth to palladium. The ARPAs, etc., say it's a topological, so we try to make that material. The material structure is shown there. It's a layer structure. All right? So we make thin film because we need a pattern ring. So this is a polycrystalline ring. Polycrystalline material is all C-axis oriented. So it's polycrystalline, but every grade is C-axis. And TC respectable, 3.3. Okay, this is the TEM cross-section showing that it's a C-axis oriented. And you make a ring. Okay, this is the background. I remove the background showing below. I enlarge it over there. You look at the minimum. 1/2, 3/2, 5/2. It's a triplets. This is the first time half flux had been seen in polycrystalline sample. Okay, all right. So it's good, but you need to do additional things, right? So this comparing with integer flux. So we have to do several rings to make sure we see that, and we have to make sure there's no trapped flux. You can send the current this way, that way, send the field this way, all checked out. So it's half flux. Now, we have to realize, why did you get a half flux? Because you have a phase change. You also have a phase change if you have odd number of phase change. But if you have even number of phase change, pi plus pi is 2 pi. You should not have any half flux. So you better see integer quantization as well. So we need to see both. So you need to make many, you see both. Okay, of equal probability. So we make 21. 13 is not equal to 8, but 13 is approximately equal to 8 because of small number fluctuation. If you make 2100, it will be half and half. So it survived the second test. There's a third test. You can also make epitaxial film. Those of you who make film know. You choose the right substrate, you can make epitaxial film. When you have epitaxial film, there's no grain boundary. You better not see half flux. So we make 30 epitaxial ring. We saw 0 pi. Everyone is, it's an integer flux. Okay, so we can say for sure this is a triplet superconductor. So there are 3 criteria. If you have a singlet, forget it. You'll never see half flux under any circumstances. If it's a triplets, you will see half flux when you have polycrystalline some of the time. The other half of the time, you should see integer flux. When you have an epitaxial ring, you should see 0 half flux, all integers. It survived all 3. So I know, okay, at least I can tell my mother, I got a triplets, okay? It's good, but it's not good enough. Why not? Because Singlet always integer. Triplets have half integer, half integer. When do you say you have found a triplet? You do one ring is not enough. 2 rings is not enough. You at least should do 10 rings or so, and can say, most likely this is a triplet. If there happens to be a singlet, you see 1 ring integer, another ring integer. When do you say it's the integer? I think you need at least to do 10 rings before you can say for sure it's a singlet. I don't like that. I like to do 1 ring and do 1 measurement and say it's a singlet of triplets. Is there any way? Yes. You can follow what the theorist said. This is the left is the theorist. The right is the experimentalist. You make a triplet superconductor connected with a singlet. The 2 opposite ends of the triplet must change sign. I don't care which side change sign, it changes sign. Therefore, this ring will have half flux. No other choice. Of course, this superconductor has to be a single crystal or a epitaxial film. So you will do 1 measurement, you know. Always half flux. Not because the S wave is connected to the opposite end. If you change to a different structure on the right, the S wave connect to the same side, you'll never get half flux. You always get single. So these 2 experiments, you only do once, you know. So direct observation of parity with only 1 measurement. So this is what experimenters need to do. You first made an epitaxial bismuth palladium, then you etch to this thing. Then you make a niobium connecting the other. My postdoc and I both knew how to do this. So he tried it, failed. I tried it, failed. Another person tried it, made it. So it's made. On the left is the GLB ring, composite end. The bottom is on the same side. And so you know it's connected because if you measure, there are 2 transitions in the same ring because there are 2 superconductors. 1 niobium, 1 bismuth palladium. So you measure this is half flux. 1 measurement is already half flux. Okay, you don't have to worry about, did I get the 0 correctly? You don't have to worry, okay? Because the ring has the imperfection. They show up on both sides. So it tells you where the 0 is, okay? Even though we know the 0 because this field is large enough, right? So 1 measurement we know. It's an parity triplets. Now, if you connect to the same side, you know that too. You actually know nothing. This is always a singlet, integer flux, because they connect to the same side. So now I do have a method to tell you I have definitely can tell this is a singlet or triplet. 1 structure, 1 measurement. Since this thing has 2 superconductors, what I show you is at the TC of the triplets. If you now you measure, it's half flux. If you go slightly higher temperature, the bismuth palladium already go normal, but it becomes a superconductor because of the proximity effect. What proximity effect? Due to niobium. Niobium is slightly higher. It will form what? Integer. So in the same ring, you can see half integer at low temperature, integer at high temperature. Okay. So if you make the other one, you will see nothing except integer. Nothing. Always integer. Right? So now we have a method called the GLB composite ring. You only make 1 ring. If it's successfully made, you make 1 measurement, you can tell the world. It's a singlet or triplet. And you should do D-wave too if you want to. Unfortunately, that's already been done. I mean, 2 decades ago. Otherwise, we could do D-wave too and show it's a D-wave, right? So it's unequivocal. 1 measurement on 1 ring, you're done. Okay, let me thank the people who did the work. Those of you who know my group know that my group has always been very small, 2 or 3 people. In this case, 2 people did it, right? And they are already moved on to greener pasture. And you finally started the work. And Chia-Ling is the one has the magic touch. She made a composite ring possible. Okay, let me summarize. I think I'm within the boundary. Well, although the chairman is getting up.
No, you still have 10 minutes. It's just. Yeah.
Okay. All right. I hope I convinced you. Half quantum flux is a phase-sensitive measurement that can definitively tell you a superconductor is a singlet or triplet by measuring the gap symmetry, odd or even, right? I did not have time to discuss. There are certain superconductors have no inversion symmetry, therefore can be neither singlet nor triplet. Must be a mixture. Therefore, always will have a triplet component. These superconductors also exist, but we won't discuss that. So, if you can start with a polycrystalline material, as I've done here. You will see 2 kinds. You will see, if it is a triplet, you will see half flux and also integer flux. Roughly half and half. But if this is a singlet, you will never see half flux. Always integer flux, right? If you make an epitaxial of any superconductor, you never see half flux. Always singlet, always integer flux. The more difficult but more definitive is the GLB ring. It's a composite ring. You make a ring out of 2 superconductors. One of them is the one you want to know. The other is a garden variety niobium. Then after you made it, you do one measurement. If you see a half flux, it's a triplet. If you see integer, it's a singlet. That's it. Thank you.
Thank you so much for the wonderful talk. We have time for questions. Did I miss
Yes.
anyone?
Can you do this measurement with strontium ruthenate?
I don't want to do strontium ruthenate. We can. I don't. Okay? For the reason is, I know Maino. He discovered strontium ruthenate. So already other experiments show it's a singlet. Why do I want to kick him again? All right? So I don't want to do that experiment. If I should do the experiment and find out it's a triplet, I'll publish it immediately. But if it's singular, I don't want to do that. Why do I want to hurt him again? That's the reason. Okay? That's all. That's all. Right? I mean, maybe you will share similar, okay?
Another way to ask the question is, if you need a magic touch to make these rings,
well, because
will you be able to do it with most material?
The magic touch is really, when you try to do it, you want to connect the S wave on the 2 ends. This is the tricky part, okay? And we, of course, she told us what she did. So we don't need her to do the magic. Okay.
Maybe naive question, that the strontium ruthenate, the T-dependent night shift, the recent result, does it already really disprove that it's not?
Well, they show a very strong temperature dependence.
But does it follow the S-wave type of exponential
Well,
suppression?
they did not say whether it's an S-wave or not, okay? But they say this is not a demonstration of triplets. So I personally don't know whether it's a single or triplets, but such measurements like the one we did could tell. But as I explained already, I really don't want to do that experiment.
Maybe 2 comments. One is that, sorry to repeat this strontium ruthenate again, but it would be interesting to check it for D wave, because your technique also says if it's S or D, or
So
I think for
okay,
that,
so which one you
Strontium
mean?
ruthenate.
Whether it could be D wave?
Yeah.
Of course, it could be D wave. You can form a 90 degrees.
Yeah.
Okay.
So that you're
But again, if it's D wave, of course, that would be very interesting. But my fear is, if the results already published, since it's a singlet, okay, it could be D wave, but okay, it would be very interesting. But I hesitate to do such measurements. All right? I don't want hurt people's feelings.
But to that point, so the technique for fabrication, this what is it MBE? What kind of deposition technique are you using? And can
Well,
it be
we
done
use
for
sputter deposition.
sputter,
The
okay.
deposition could be anything. You could use MBE, you can do it.
So this
it-
can be done on oxides as well, right?
Yeah. It can be done on oxide. Oxide is trickier because of the oxygen problems, okay? But in principle, it can be done, all right? So if you try hard enough, eventually it will work, okay? But the message I try to convey is there are ways you can definitely tell. You know, my conclusion, the old thermodynamics measurements are not reliable, right? It's been going on for a long, long time.
Great, thank you so much. If we don't have other questions, we will move on so we can catch up on time. Thank you so much.